In this video, I would like to share with you a couple of iterative methods that we use for solving system of linear equations. In the previous cases or example that I covered in solving one-dimension heat conduction problem using the backward and central finite difference methods, I solved the system of linear equation using the matrix approximation, which is A X matrix to the equal to the B, whereas A is the coefficient matrix and B is a free term matrix. Then you can get X from getting A minus 1, the inverse of the coefficient matrix times B. And we did that with MATLAB. We got the solution for that. Let's recover these the system of linear equation that we solved using MATLAB. In the previous one was 20 minus 2t1 plus t2 is equal 0. And for the second equation, t1 minus 2 t2 plus t3 equal 0. t2 minus 2 t3 plus t4 equal 0. t3 minus 2 t4 plus t5 equal 0. Then t4 minus 2 t5 plus 100 equals 0. This is the system of linear equation that I solved using MATLAB in the previous two examples. Now I would like to do some iterative method, which you can either write a MATLAB code for it, or you can actually simply use Excel to solve. So there are two major iterative methods that we use all the time, and you can classify the iterative. There is more than two, but I'm talking about the simplest one that you can use quickly. This is not a numerical class, but I would like to introduce that as a matter of review for those who are aware of or not really aware of these kind of technique as a reminder. So the iterative methods can be classified under either it's explicit technique or explicit method, and the other one is actually called the implicit, right? Explicit or implicit method. So in the explicit method or the implicit method, I will explain each one through the example here. So let's start with the first one, which is the explicit method that you can do that very easily, very quick using Excel sheet. And this method is actually simply the Jacobi method is the simplest one. And the implicit method I'm looking for is simply Gauss-Seidel iteration method. You want to call it Gauss-Seidel, Gauss-Seidel, different way of pronouncing it. I think what's more important, how you apply it and how to use it. So let's start with the Jacobi method, which is, as I mentioned, it's an explicit method to solve system of linear equations. So this is my system of linear equation. I'm going to call the A. I'm going to start with Jacobi method. And when you look to the technique we apply, you will understand why this Jacobi method is called explicit and Gauss-Seidel or Seidel is implicit technique. Explicit means that when you calculate the data at specific situation, or a specific iteration or specific time step or whatever you are doing, you're gonna just need the previous set of data you obtained in the previous step. So you are marching one step at a time. To calculate the current data, you need the data before. So data at specific iteration can be obtained by previous iteration results. So you are marching step by step. You get the data for this step using the previous step. Then you take that current one to get the next one. So iteration number 3, I will need the data I obtained from iteration number 2. Iteration number 6 only need the data from iteration number 5. Okay, there is no cross-linking here. So one step at a time to get your data. Let's see how to set up your system of linear equation and how you solve that problem. So this is a set of equations that you have. What you do, you pick any equation you want and keep one variable to the left side and put everything into the other side. I would like to move in an order here. So what I'm going to do, I'm going to take the first equation and I will try to get T1 setting aside and put everything in the other side. So for the first one, I will say, okay, I will bring that term to the right-hand side. So I will have T1, and there is 2 here, so I'm going to divide by 2. So I'm going to get actually 0.5 T2, right? Plus 20 over 2, that's going to give me 10. So this is reformatting node number 1 equation here. Now let's go for the second equation. I will isolate T2 to the right side. So I will have T2. I will divide by 2 both sides. So I will have 0.5 of T1 plus 0.5 of T3. Next equation, I will isolate T3. So I will end up having 0.5 T2 plus 0.5 of T4. Next equation, I will isolate T4. I will have 0.5 T3 plus 0.5 of T5. In the last one, I will isolate T5. So I would have 0.5 T4 plus 100 over 2, or multiplied by 0.5, I will get 50. So this is the new arrangement of the system of linear equations I have. Now I have T1, T2, T3, T4, T5 on the left-hand side, but all of them are function also of the other T1 through T5, right? So what we're going to do, we're going to call this what I need to get at the new iteration. I'm going to call that iteration P1, well, P plus 1. So that's my data I need to calculate at iteration P plus 1. So according to the definition of Jacobi or the explicit method, to get the data at specific iteration, you need the data from the previous one. So every piece of information here is obtained at iteration number B or iteration P. So that's P, 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 that's P. So if you need to get the information at iteration 10, you need all the data from iteration 9. Then if you want to get at iteration 11, you're going to need the data from iteration 10. So you are marching step by step. So the big question is, what if I would like to get the data at my first iteration? Oh, this means that I need the data from the previous one, which is iteration number 0, or before the first iteration. And this will be an assumed value. So all what we do, we assume an initial data. Then I will use that initial data as the data of iteration 0, and I will calculate the iteration 1. Then the results of 1 obtained from 0 will be used again to get iteration 2. Then you take the data from 2 to the right-hand side to get the iteration of 3. So each data point is used to calculate the next step here. So let's try to see how this actually looks like. So let's assume I'm going to create a table. That's the best way to practice that solution here. You're going to actually create a table. You're going to list the values of your temperature, T1, T2, T3, T4, and T5. And I will have my iteration or iterative values listed as I go here. So I will start with iteration 0. That's my first iteration, which I don't have data for, but I will assume the value of all the temperature is 0, 0, 0, 0, 0. You can start with any assumption, but 0 will simplify everything. So now I will take that iteration 0 to the right-hand side of these equations, and I will put T2 is equal 0 in the first equation. I got T1 equal 10. Then T1, don't use this one. You want to calculate T2 in this equation, you have to use everything on the right-hand side from the previous iteration. So I'm still have T1 is 0 and T3 is 0. So I'm going to use T1 is 0 here. I'm going to use T3 is 0 here. I'm going to get T2 equals 0. For the next equation, T2 and T4, both are 0 values. I'm going to get T3 equals 0. Then you go for the next one, pick T3 and T5 from the previous one, T3 and T5, 0 and 0. I will substitute, T4 will be 0. If I go to the next equation, I need T4 from the previous step, 0, so T5 will be 50. That's my first iteration. Now, you forget that line, you forget these data. This is now your previous step. Use all these data to substitute in the right-hand side of this equation and get the new value. So that's iteration number 2. I will go into the first equation. So I'm going to have 0.5 times, I need T2. T2 from the previous one is 0 plus 10. So I will end up having, this is still 10. Now, go to second equation. You will take T1 from the previous step, which is 10. So I will have 0.5 times 10. I'm taking that T1 plus 0.5 times T3. T3 from this step is 0. So I will have 0. So I will end up having T2 now is coming to be 5. So now 10 is still the same, but now 0 becomes 5. Now let's go to the next one. I will take T2 and T4 from the previous step, this value and this value. So you'll have 0.5 times 0, 0.5 times 0. In this equation, you will end up having this 0. You go for the next equation, you need T3 and T5. T3 and T5. So this equation will be 0.5, T3 is 0, plus 0.5, and you'll pick T5 from the previous step, which is 50. So I'll end up having 25. So for that iteration 2, I'm end up having 10, 5, 0, 25. What about the last equation? T4 from the previous step is 0, so I'm end up having 50. So the final value here is 50. You see the change now? 0 becomes 10, 10 remains 10. 0 becomes 0 and becomes 5. 0, 0, 0, 0, 0, 25, 0, 50, and 50. Now we are marching. Now, if I want to go for the iteration number 3, for the first equation, I will have 0.5 times T2 from where? Not from here, not from here, just from the previous step, which has a value of 5. So 0.5 times 5 plus 10. Then go to the second equation. It's 0.5 times T1 taken from the previous step is 10 plus 0.5 T3 from the previous step is 0. Now, next equation, this equation here, 0.5 times T2 from the previous step is 5 plus 0.5 times T4 from the previous step is 25. Then, next equation, 0.5 of T3, it is 0 in here, plus 0.5 of T5, it's 50. Then, last equation, I will have 0.5 times T4, which is 25, plus 50. Let's see what are the new values here. So that's 2.5, so I'm get 12.5. Here I'm getting, that's 5. Then I'm getting 2.5 plus, so that's 30 times 0.5, right? If I take 0.5 as a common factor, that's going to be what, 15? Then I will get here 25. Then you will get here half of the 0.5, that's 12.5 plus 50, 62.5. Is that correct? It sounds like, yep. So if you look to the iteration, zeros, 10, 0, 0, 0, 50, 10, 5, 0, 25, 50, 12.5, 5, 15, 25, 62.5. So you keep doing that all the way until you reach a certain margin of error between the same value, but a different iteration. For example, the error here is 10 degrees. Error here is 0. Error here is 2.5, right? So I have to keep trying until the difference between one iteration, let's say this is iteration X, and this is iteration X plus 1. You got the difference between the values here within a certain epsilon value. Let's say that you set up your epsilon, the error value is 0.1. If the temperature change only by 0.1, I will end up having, this is my iteration. Then you do the same for all of them. You cannot be picky. If this is iteration X, this is iteration X plus 1. It's okay. T1 was, I'm satisfied with the error at that X plus 1. But for T2, I'm satisfied with X plus 2. No, you can't. You have to meet that criteria for the same iteration to all these values. Okay? So if you keep iterating all the time, I think I reach at iteration 64, 65. I found that epsilon, it's very minor. I think I reached 0.01 at iteration 65. This is at iteration 65. I got the following values for the 5 temperatures. I got T1 is 33.33, T2 is 46.66, T3 is equal to 59.99, and I got T4 is equal to 73.32, and I got T5 is equal to 86.66. You guys recall what was the analytical solution values or the finite difference values for that same example here? We got before, let me recall these numbers for you guys. We got T1, 33.33. We got T2, 46.67. We got T3, 60. We got T4, this is degree C, and this is degree C. We got T4, 86.67. We got T5 is equal to 73.33. This is from either the backward finite difference method or from the central finite difference method or from the analytical solution. So now let's compare what we got. You see that T1 is matching very nicely after 65 iteration. Now, you see that there is difference error here of 0.01 degree. I have a difference here of 0.01 degree. This is, actually, this should be 5. Sorry about that. This is 4. So if you compare this to this and this to this, you will find that you're still within the error of 0.01. So 65 iteration, it showed the error of 0.01 compared to the analytical solution, which is very good agreement with the analytical solution. But the downside of it, it's cost you 65 iteration. You cannot do that manually. That's why you either write a MATLAB code or you simply use an Excel sheet. I will try to upload an Excel sheet for Jacobi method into the first comment of that video so you can actually download that Excel sheet and use it. But I think I use that Excel sheet for the same problem here. I don't mind to share that for anyone interested to have that Excel sheet set up to use it for the upcoming experience. So that's conclude the explicit numerical method Jacobi for solving a system of linear equation. That's conclude that recording for this example.